Good afternoon, everyone. You're very welcome to International GIS Day 2016, where we'll be hosting our webinar on using QGIS to automate flood depth and extent data via QGIS's Graphical Modeler interface. So my name is Ian Hand, and I'm GIS and Remote Sensing Specialist at Mallon Technology. I graduated from Trinity College Dublin in 2012 with a BA in Geography, and then went on to graduate with a Master's in GIS and Remote Sensing in 2013 from NUI Maynooth. Since graduating, I've accrued over 3 years of industry experience where my actual specialties would involve land use and land cover data generation and analysis, and also flood risk management and flood hazard data analysis. So a mixture of GIS and remote sensing areas. Also, we're very pleased to say that the Royal Geographical Society has approved today's webinar for accruing CPD credits for their Chartered Geographer accreditation. So today's webinar will consist of a brief overview of flood hazard and risk assessment in Ireland, and then followed by step-by-step demonstration of Quantum Graphical Modeler for the automatic generation of flood depth and extent data. So national flood risk management in Ireland. Well, the national picture is basically administered and carried out by the Office of Public Works, the OPW. So these would look after flood hazard and risk assessments on behalf of national government flood management policy and on a higher level, the EU Floods Directive in general. So as part of that, we have a contract with the OPW where we specialise in producing flood hazard and risk data. We produce the data themselves for maps, and we also do a bit of analysis in terms of buildings and population that will be affected, etc. So predictive flood modelling is a key component of the task carried out by the OPW themselves concerning national flood risk management. So flood depth and flood extent generation. So the QGIS Graphical Modeler, this is where this comes into its own really. So producing flood depths and extents manually, it's a very lengthy process with multiple stages of inputs and outputs before final products. It's a very manual, laborious process. So the Quantum Graphical Modeler essentially automates this complex process and producing final products from original inputs. So if you can imagine, the first input maybe, might be flow and water level data, which is taken in the field. You then have to interpolate that in one algorithm. You then have to take current LiDAR away from that. You have to rasterize things, polygonize. So these are all separate algorithms in their own right, but they all produce different outputs, which then become different inputs of successive algorithms. And doing this manually, you can imagine it's quite costly on labor and time. However, the QGIS Graphical Modeler, you can actually take all these algorithms and you can create one seamless chain of algorithms where you essentially only have your original inputs, you press run with the modeler and it produces your final outputs. So there's no actual messing of different stages of inputs and outputs. It's a one-stop shop. So the actual modeling inputs for flood depth generation and flood extent then. So your very first protocol is your nodes input. So in particular, these nodes contain data on predictive water level for future flood event scenarios. So these would have been generated by a dedicated team of flood modelers who are based out in the OPW. And again, essentially the nodes, they contain X, Y, and Z data. And the Z data is essentially predictive water levels based on various things such as climate change, previous flood events, etc. The second input is process and extent. So you're basically going into GIS and you're telling what extent you'd like for the processing and interpolation of the nodes data above. Third input is LiDAR. So you need to obtain current LiDAR data where you'll use as a baseline for the current scenario, and you'll then take that away from the interpolated nodes data, which will give you your rough flood depth output before it's cleaned up. And finally then you have an attributes file, which is in CSV format, which contains attribute fields for your flood extent. Again, you join this in while you're running the model, so your actual output it'll be complete with attributes. So there's actually no manual generation of attributes. It's all a one-stop shop. So we'll now go to Quantum itself. So here I've loaded already the actual nodes data here. Again, it's just simple nodes along the course of a river. You have X, Y, and Z data. So as you can see here, just X value for your X, Y, and Zs, basically. And then also you have the current LiDAR data here, which is just being colorized and styled here. So if you're blue, which is low, green, and then your highs being reds. So these are the two real main inputs into your actual model. So before we actually run the model itself, you need to set up various parameters in the Graphical Modeler. So you go into your Processing tab here and go to Graphical Modeler. So this is now the interface for actually constructing the Graphical Modeler, which will be your one-stop Geoalgorithm, which will contain numerous algorithms. So there's two main components to this. You have your inputs here and you have your algorithms. Your inputs, again, you have your nodes input, your processing extent, LiDAR, and your attribution file. So all these, you have your table there for your attributes and your nodes. Your raster layer will correspond to the LiDAR, and the processing extent then can be found in extent. And then the algorithms tab, these are essentially all the different providers that provide the actual tools which you'll use, or the algorithms, which will actually make up the final flood depth and extent model. So our first step is setting up the actual inputs. So we'll start with the nodes first. So this is in table format, it's a CSV. You just single click here, hold down, and bring it into your window here. So your parameter name, we'll call this nodes input. And it's required, click OK. And this is your very first component of your flood depth and extent model. So next to your processing extent, let's call this processing extent. Okay. Then you have your LiDAR input, which is our raster format. So we just call that LiDAR input. And finally, you have the attributes file. So we just call it attributes. And input. Okay. So these are the four core inputs into our model that we're going to be building today. So next we'll start actually adding in the individual algorithms or tools which will make up our final model. So we'll first start off with a points layer. So essentially we're going to transform our CSV nodes into virtual shapefile points, because we need this in order to interpolate. The interpolation will not interpolate CSV alone. It has to be a virtual shapefile layer. So the easiest way to find the tool we need is your search engine here in your algorithms. So you just click into it and start typing in points layer. So here we go, points layer from table. Again, select and drag it in. So our input layer will be our nodes input. Our X field in this case is E for easting, and our Y field is N for northing. Our target CRS in this case is Irish Grid. So EPSG 20902, we select that, click OK, follow by OK. So this is now your points there from table. Next, we need to interpolate these points. So we're going to use inverse distance weighted. So just again go to search engine and start typing in inverse. And we're going to use the Saga provider tool here. So inverse distance weighted by Saga. Throw it in. And the output will be our points there from table. So it already automatically recognizes this will be the input, as it's the only virtual shapefile here. The rest are CSVs. So our attribute in this case will be Z. Distance weighting, inverse to the power 2. Yep, this is fine. Just leave this as default. Our actual search radius will increase to 1,000. So this means for every point that's interpolated, there will be essentially a 1 kilometer radius, which will be interpolated around each point. Our cell size we'll change to 2, so 2 meter resolution. This corresponds also to resolution of the LiDAR data. And our output extent will be processing extent, which we will set later on. So click OK. And so our third algorithm will be Raster Calculator. So just type in Raster, and Calc. So we're going to use the Saga Raster Calculator here again. And for this one, we're actually going to take away the current LiDAR input from our virtual interpolated water level layer. So the main input layer will be the algorithm, the output from the inverse distance weighted, and our additional layer, which will essentially be our B layer, will be LiDAR input. Okay. So the formula, the particular syntax that Saga would prefer for this is just open bracket underscore A minus underscore B. Oh, sorry, I mean non-capital A minus B, close bracket, and our output is 8-bit. So that's okay. So you can see it's shaping up quite nicely here. You can see how it's working. It's joining the inputs to the algorithms. So it's basically it's a nice graphical interface. So our next input, again, we'll use a Raster Calculator again, but this time we're going to use it to create a Boolean raster surface from our newly derived output from Raster Calculator. So we essentially want all data that's above 0, and this will actually generate the first step of the initial flood depth raster, which we'll use in the very end. So just for confusion, or to avoid confusion, we'll call this Boolean extent. Okay. And so our input is calculated from the Raster Calculator, and the formula this time, so the syntax for this is G1 greater than 0. And our output type is 2-bit integer, because basically a Boolean data is made up of zeros and ones, so it's 2 bits. We just need 2 bits. 4-bit and 8-bit is excessive for this, we don't need it. Click OK. So our next step is to actually polygonize the 1 values from this Boolean extent, and this will start to shape our flood extent, our vector flood extent output. So we'll just type in polygon. And here we go, vector geometry tools. Use GDAL. Raster to vector. So our input layer is the calculated from the Boolean extent. Output field name DN for digital number, that's fine. Click OK. Our next step now is to select all the 1 values from our virtual polygonized Boolean extent. So we'll use our select by expression tool here. So we'll just type in select by and exp for expression, and here we go. Select by expression. So our input is the polygonized raster to vector, and the actual expression itself is dn equals 1. So this creates a selection. This is all okay. And we now want to save that select expression that we just created. So type in save, and here we have save selected features. So again, it automatically recognizes we want to save select by expression, so that's fine. Click OK. So you can see again, it's shaping up now to be quite a complex algorithm here, so bear with me. So now we have our next step, which is field calculator. So we're going to create a new field for our stage selected features output. Just type in field and calc. So here we have our field calculator tool. So our input layer this time is from the save selected features, which we just did. And our resultant field name will be FID, which stands for feature ID. So we're basically creating unique IDs for our polygons. This will tie into when we join in the attributes data. So they'll have two FID fields with Mario per each other, which will create the join, which is what we need. So field type float, we leave that, that's fine. Field length 10, we're only dealing with numbers here, fine. Our field precision, we don't really need any because we're not dealing with real decimal numbers. We're just whole numbers, so 0 is fine for this. Create new field, yes, and perhaps most importantly, our actual formula. In this case, we're going to use the wildcard $sign and underscore or under caps ID. So that's fine. Click OK. Our next is now to join our resultant field calculator output with our attributes file. So now we type in join, and we've joined attributes table. So again, recognize it's calculated from field calculator. That's what we want for our input. And our input layer 2 is attributes input. So all that's fine. Our actual table field that we want to join is FID, and our second table field will also be FID. So these are the two fields that both the attributes input and the field calculator output share in common. So this will essentially create the join. So this is fine. Click OK. And so for the final float extent vector now, we don't actually need the DEN field and the FID once the join is completed. So we're going to delete these fields for our final layer. So we just type in delete. That's delete column, which is essentially deleting your field. So we have our input, which is the join attributes table output. Our field to delete in this case is DN. And click OK. And we're going to add in one last delete column tool. In this case, it is our previous delete column output input, and our field to delete is FID2, which is the second FID column it would have created during the join. So click OK. Now, at this point, our actual flood extent vector is actually created, it's ready to go. So in order to create it as a final output, you need to go back into this final delete column and delete a column output vector, give this an actual name. So in this case, we will call it output float extent vector. And it's now generated a blue box, so this means this is the final output of the model, which is what we want. So now we have to just tidy up our actual raster from our raster calculator and our inverse distance weighted to create the final flood depth. So here we're going to clip raster by mask layer. So we just type in clip. Let me just go raster. So here we go, clip raster by mask layer, so just GDAL. Again, one of the main benefits actually of using this QGIS graphical modeler is that you have so many different algorithm providers. You've GDAL, you've GRASS, you've Saga, you've the quantum core tools themselves. So it's a really powerful array of tools that are right at your fingertips when you're creating this. So it's a real plus to have access to all that. But anyways, sorry, bit of a segue there. We'll go to our clip raster now. So our input layer, our input layer is our result from Raster Calculator. and our mask layer is the output from the original save selected features. So again, this is just really tidying up the resultant raster calculator, which will create our final flood depth raster. So you leave these as default, which is fine. However, you're given an output name because it's one of the final outputs out of the two. So in this case, we'll call it output flood depth raster. Click OK. And there you go. You have our two outputs from our 4 original inputs. Now, if we didn't have the ability to produce this graphical modeler, and if we were doing all this manually, every single step here, all the individual algorithms would have to be run manually through the main quantum interface, and would produce their own individual outputs, which you'd then have to use for the next algorithm as an input. And so it's a manual chain, a manual stage, different inputs and outputs. It's a lot of time, and you have multiple data then to keep an eye on. So this essentially is an excellent cost-cutting measure in terms of time and effort, really. So our final stage to save this off as an actual model is to give it a name. So we'll call this flood depth and extent generation. And you just have to give it a group then, which will form a quantum graphical modeler group where all your models will be stored. So we'll just call this floods models, which is fine. So next you just click the save button here. And well, I actually saved one earlier, so it's flood. You just call it flood depth and extent generation, and this is saved as a dot model format. So this is the format Quantum will store your graphical modeler in. So you just click save, and it'll be correctly saved. You can then X out of this. And now to actually access your newly created graphical modeler, which will be your one-stop algorithm for flood depth and flood extent generation, you have to go back to the Processing tab. This time, instead of clicking on Graphical Modeler, you click on Toolbox. So this brings up Processing Toolbox. Now here already I've recently used algorithms that I would have used throughout the week, and you also have the various providers for GDAL, GRASS, Saga, Quantum itself. And here, and already I had something searching there earlier on, inverse distance weighted. Just clear this, and here you go. So you have a models drop down here, and we have a flood models group that we would have created a step or two ago. Drop down, and here we have it, flood depth and extent generation. So you actually double click on this. This is the actual end interface for your modeler. So it's actually quite nice. You know, it's quite slick. It looks like a typical core algorithm that you'd associate with Quantum or any other GIS. So the finished look is actually quite nice. So here you have your LiDAR input, which is our shore mosaic. This is actually the LiDAR data was actually kindly provided by the OPW. So this would have been when I was working on generating flood depth and extent data for the shore river catchment. So we just select this. Our attributes input, we have to navigate to this. So it's attributes. So these are preset fields and attributes under guidelines, GN26 guidelines, which basically adhere to EU standards in the capturing and monitoring of floods data. So you click open anyway to put that in. And our nodes input, in this case, is M1A underscore Q1000D. And the Q1000 basically stands for flow 1000 year. So this would be a future flood event scenario, a 1 in 1,000 year chance of it happening. The actual production of flood depth and extent data, it ranges from 1 in 10 year, 1 in 100, and 1 in 1,000 year for fluvial events. So it's quite a lot of data to generate. So your processing extent this time, you click this little browse button here, select extent on canvas, and just zoom out a few scales, and then hold down on the left click and create a bounding box here, and then just lift off the left click, and there you go. So there's your processing extent here. Then your output flood depth raster, just save the file and output wherever you want really. So I'll just go to C drive and just call it flood depth. And your vector, do the same, flood extent. And then you click run, and it goes away. Now, depending on the size of and extent of your actual data, now if you're dealing with a whole river course, it will take some time. However, if you're dealing with small sections of a river, it should take only a couple of minutes to run. So click run, and your actual outputs will look similar to this. So here you have our actual flood depth here. So this is for a section of the shore. We'll just zoom in. So as you can see, this is color-coded. I would have color-coded earlier on. And so the red would correspond to depths, which would be 1.6 and greater. So it'd be quite a dangerous zone to be flooded in. And then the lighter the color to blue, the safer it is. But however, it is still flooding. So if a house or a property was actually within this flood zone, insurance companies will use this to determine whether or not to pay out in premiums, etc. And then flood extent data itself is the actual extent of the flood. So it's a vector extent essentially. So there you go, you have your flood depth and your flood extent. So again, if you were to do this manually, it would take an awful lot of time and effort. Multiple individual algorithms with various inputs and outputs, all agglomerating together in various different stages. So it's quite costly in time and effort. Whereas with your QGIS modeler, it's very quick, very efficient, making a complex string of algorithms very easily accessible as an end product. So before I finish up, I'd just like to say a few acknowledgements. So first of all, I'd like to acknowledge the Quantum project, so the Quantum GIS project itself. Quantum is an actual free and open source GIS program or piece of software, so anyone can download it and use it. So if you just go to their website here, here we go. So free and open source, you can discover Quantum here. Shows you various different examples of what you can do. There's a lot of tutorials online as well, and most importantly, you can download Quantum here. So yeah, your most recent version here, you can download now. So I'd highly recommend it for anyone who hasn't already to download Quantum and become a user of this excellent free and open source software. And finally, I'd also like to acknowledge the Office of Public Works for their assistance in this webinar for providing the LiDAR data and the actual nodes flood modeling data as well. It's greatly appreciated. So useful links, you have the Quantum project link already, which I showed you, where you can download Quantum and use yourself. The OPW also has an actual maps and data applications website. So it's maps.opw.ie. And here you can actually find the flood risk management plans and the actual maps which contain the flood depth and flood extent data which I was talking about. So, wherever you're living in Ireland, there will be maps produced for the main river catchments. So it's well worth checking it out to see exactly what's predicted in terms of flooding for your area. And these maps will also feed into actual scheme building, flood defences. And then, as a result, you can check their defended areas. So it really is it's a wonderful website, and I'd highly recommend you check it out. And finally, the Mallon Technology YouTube channel, you can actually find our previously recorded webinars, as well as this one in due time. And you can also find other videos and tips which Mallon would have produced. So here we have our previous one, so using Sentinel-2 imagery, getting started with Sentinel. So yeah, watch this space and watch this this channel in particular for future webinars and future tutorials. If you have any questions, you can type in your questions using the webinar question box, or you can email marketing@mallontechnology.com if your query is slightly more in-depth and technical. So that's it for me. Thank you very much for attending today's webinar, and enjoy the rest of International GIS Day. Cheers.